In this video, we're going to discuss the concept of frequency response functions, which give rise to a type of figure commonly known in the literature as bode amplitude plots. It's also closely related to the concept of transfer functions, which you might encounter in a class on systems or control engineering. To begin, we're going to look at an example of the second order equation y double prime plus y equals sine omega t, where omega is a parameter representing the input angular frequency. When omega is 0.5, we can see that the solution is periodic. It's in fact a combination of two sine waves of different frequencies, and it has a maximum amplitude of around 2. As I increase omega towards 1, let me make a jump to around 0.75 to begin, we can see that the size of the maximum amplitude starts to grow as these beats get a little bit more irregular and the dips become a little more infrequent. Increasing omega even further to 0.9 leads to now these sort of beats that have a maximum amplitude of around 10. In fact, if I look at this on a longer time scale, you can see this pattern continues on into the future. If I increase omega again to 0.95 now, I can no longer see this graph on the given set of y limits, but if I increase my y limits slightly to around 20, then we notice that the amplitude has now increased and the length of period, the time period between beats has also increased, but they happen nevertheless. Now, of course, we talked about in class that the resonant frequency for this system is omega equals 1. So as we get closer and closer to 1, notice that the amplitude of our solution grows and grows, so that I have to sort of look at a sort of zoom out of the window more, if you will, to see actually where the peaks lie. In this case, it looks like the peaks almost go up to 100. But nevertheless, if I look at things on a long enough time scale, I will still see the same pattern of beats emerging. Even if I go to 0.999, right, and increase my y limits all the way up to close to 200 here, that's still not enough to see this. However, if you increase the time scale, you'll notice that we eventually do see this beat where the solution dies back off after a finite amount of time. It's only that sweet spot where omega equals 1 that we actually see these growing amplitude oscillations. So in this scenario, even if I increase my y limits as much as possible, and even if I increase my time scale as much as possible, well, at least as given by the parameters in this app, then our solution will just continue to oscillate with growing oscillations over time. So the idea behind frequency response functions is to take all these different plots that we get for different omega and to summarize them by a single point which tells you for that value of omega what was the maximum amplitude that I achieved. The code below this app is an example of how to do this, and I'll post some links to this code and the as well as the app that I just showed you in the video description. But what we'd like to do is we'd like to choose a sequence of values for omega and solve the differential equation for each of those values, which is something we can do explicitly. But instead of storing those solutions, I'm only going to store the maximum value of each of those, and I'm going to relate that to a point that corresponds with omega, and then plot that on the y-axis in a graph. And so the result looks something like follows. We see that as we approach 1 from the left, we get this rising peak, so that actually at omega equals 1 we receive a pole. And as we approach 1 from the right, we see the same type of behavior emerge. To reiterate, our goal is to summarize all the different plots that I might get from solving our differential equation with different input frequencies omega into a single function f of omega, which describes the maximum output amplitude that we get for that input frequency. To achieve this goal, we're going to look at particular solutions to our standard second order constant coefficient equation m y double prime plus gamma y prime plus ky equals g of t, with a specific choice of g of t that summarizes all sinusoidal functions with a complex exponential. We know in this case that a particular solution which should work is a e to the I omega t, where a is an unknown coefficient. And if I plug this in for y, we obtain the relationship that for this to be a solution, I would need m I omega squared times a e to the I omega, plus gamma I omega times a e to the I omega plus k times a e to the I omega. I need that to equal just e to the I omega. So equating the coefficients of like terms on both sides of this equation, A right here is the output amplitude, except I need to do one thing. I need to take the modulus of this expression. If I can calculate this for a given value of omega, this will then tell me the answer to our goal at the top of this page. So we're going to call this function the frequency response function. Now it's closely related to two other important quantities that we encounter in this section. One is the characteristic equation. Recall that the characteristic equation, m lambda squared plus gamma lambda plus k equals 0. If I take this part and I replace lambda with I omega, I achieve the denominator in my frequency response function. It's also closely related to a quantity called the transfer function, which is what you get if you replace I omega with some other variable s in this function above. And we'll talk about that a little bit when we get to the concept of Laplace transforms. Once we've defined this function, then our resonant frequencies, we're going to define those as either poles or local maximum of the frequency response function. Sometimes we may distinguish and others may distinguish between these two scenarios and call this pure resonance versus sort of practical resonance. Meaning pure resonance is when you actually have a blow up in the amplitude, whereas practical resonance is just the optimal response that you could get. But usually we'll just refer to them as resonant frequencies in what follows. Let's start off by finding the frequency response function for our harmonic oscillator my double prime plus ky. And let's use that to compute the resonant angular frequencies for this system. The first step in doing so is to write out the frequency response function, which given the definition on the previous page is going to be m I omega squared, and note here that gamma is 0 and then plus k. And we can simplify this denominator because I know that I squared is -1, so this is just going to be k minus m omega squared in the denominator. To get an idea of what this looks like, note that the denominator, the places where the denominator is equal to 0 are when m is equal to plus or minus square root of k over m. These are what we call the harmonic or resonant frequencies for this system. They're the natural frequencies at which it wants to oscillate. If we graphed a plot of this function, let's just look at the case for positive omega, then somewhere up here I would have square root of k over m. When omega is 0, I should get a value of 1 over k, and I should have some kind of pole here, so a vertical asymptote that approaches that and then converges to 0 as omega goes to actually positive infinity on this side, and there'd be a similar pole in the negative axes as well. To look at an example where we do have damping, let's calculate the frequency response function for y double prime plus 2y prime plus 5y and use it to compute the resonant angular frequencies for that system. In this case, our frequency response function is now f of omega equals 1 over m, which in our case is just 1 now, times I omega squared, which remember simplifies to negative omega squared because I squared is -1, plus gamma I omega plus k. And this is a little bit different than the last example because notice now I have a complex number in the denominator, which means we need to interpret that result as the modulus of that complex number. The complex number in the denominator there has a real part of 5 minus omega squared, and it has an imaginary part of 2 omega, right, the part next to the I. So to find its magnitude, I would add the squares of those quantities together and take the square root. To find the critical points of this function, let's take its derivative and set it equal to 0. This function is equal to 0 exactly when 4 omega cubed minus 12 omega equals 0. To check which of these is the actual resonant frequencies, we would need to plug them back in to our function f of omega. We know that they're critical points. We also know that looking at the value of f, it goes to 0 as omega goes to plus or minus infinity. So whichever one of these yields the biggest value of f will be a local max. Since 1/4 is bigger than 1/5, these would be my resonant frequencies for the function.